corresponding equation in linear motion. This is the rotational motion, tau equal to I alpha. The corresponding equation in linear motion is F equal to ma. You see that? Linear acceleration is produced by a linear force. A rotational acceleration is produced by a torque. So, tau equal to I alpha takes the place of F equal to ma in translational motion. Alright, in that case tell me, what is the role of this I, the moment of inertia? If you noticed, in linear motion our equation will be F net equal to ma. In rotational motion, that equation becomes tau net. The best way to write this is tau net. The net torque is equal to I alpha. Look at that. F net is replaced by tau net. Linear acceleration A is replaced by angular acceleration alpha. And therefore, this moment of inertia for rotation correspond to mass in linear motion. You see that? The moment of inertia in rotational motion is a quantity that corresponds to mass in linear motion. F net equal to ma, tau net equal to I alpha. So you must understand that relationship. Alpha is the angular acceleration caused by the torque. Now this is similar to F equal to ma for linear motion. Okay. The moment of inertia I plays the same role in rotation as m plays in linear motion. Now, what is the moment of inertia of a disk? Now remember, moment of inertia is defined about an axis. Now, let me see if I can spend some time. Now, here I have an object of mass m, and I'm going to rotate it about this axis. You see, the axis of rotation is this. That is the axis of rotation. That means this is r, the perpendicular distance between the mass and the axis. And therefore, what is the moment of inertia of this particle about this axis? It is mr squared. Now, if I change the position of this mass over here, I am changing the moment of inertia. You see that? Now it is much easier for me to rotate. The moment of inertia is now less. mr squared is less. If I move it out, I'm increasing the distance r, and this moment of inertia is now greater. Now you can see I have to actually use a greater force to keep it rotating. The moment of inertia of this mass is now greater. Now, moment of inertia is always defined about an axis. Well, let's look at this disk. Now, it is easy for me to rotate this disk about this axis. Look at that. Now, this disk has a moment of inertia about this axis. You can see the axis is actually passing through its center of mass. And so, the moment of inertia of this disk about the axis that passes through the center of mass, we will call I center of mass. Moment of inertia of the disk about an axis that passes through its center. Now, can you imagine? If I want to rotate this disk about an axis passing through here, well, I'm going to hold it there and how difficult it is for me to rotate it about that axis. That means this disk has a much greater moment of inertia about this axis. The moment of inertia of a disk is the least about an axis that passes through its center of mass. If you take any other axis, the moment of inertia of that object about that axis will be greater. We will look at that in the next part of this lesson. Now look at the meter rule here. I can rotate this meter rule very easily about its center of mass. That means its moment of inertia is the least about its center of mass. Suppose I want to rotate the ruler. Now, if I want to rotate the ruler about an axis, I don't think, well, suppose I want to rotate this ruler about an axis passing through this point. How difficult it is. It is very difficult. That means the moment of inertia of this ruler about this axis is much greater than its moment of inertia about the center of mass. Okay, now you need to remember a couple of formulae for moment of inertia of certain regular shapes, and I'm going to give you that formulae. Okay, well, first of all, let's consider a disk. A disk is the most commonly used device for rotational purposes. So a disk and its axis passes through the center of mass. This Cm stands for the center of mass. It has a radius r and a mass m. The moment of inertia of a disk of mass m and radius r about an axis that passes through its center of mass. Now, the formulae I'm going to give you now are all the moment of inertia of regular objects about an axis that passes through their center of mass. Now, what is the formula for the moment of inertia of a disk about an axis that passes through its center of mass? The formula is this: I center of mass equal to 1/2 mr squared. This is the moment of inertia of a disk of radius r and mass m about an axis that passes through its center of mass. Well, this is an axis passing through the center of mass of this disk. So its moment of inertia is 1/2 mr squared. Alright, let's look at the next regular shape. The moment of inertia of a sphere. If I have a sphere like this, and look at the axis. Its axis is passing through the center of mass. And the center of mass of a sphere of radius r and mass m about an axis passing through its center of mass is 2/5 mr squared. You should be able to use these equations wherever they are necessary. Okay. Another one. What is the equation for the center of mass of a ruler like this, which has got a length L and a mass m? The I center of mass. What does I center of mass stands for? The moment of inertia about an axis through its center of mass. So I center of mass for a ruler like this about an axis through its center of mass is 1/12 ml squared. And finally, what is the moment of inertia of a hoop? That will be I center of mass equal to mr squared. We rarely use this, but a disk, tell me, what is the moment of inertia of a disk about an axis through its center of mass? 1/2 mr squared. What is the moment of inertia of a sphere about an axis through its center of mass? It's 2/5 mr squared. And what is the moment of inertia of a ruler about its center of mass? It is 1/12 ml squared, where L is its length. Well, what we have done is we have now discussed some fundamental ideas of rotation. We now know that the second law of motion is equally applicable to rotation. F net equal to ma can be replaced by tau net equal to I alpha. And you should have a good understanding of what that I, moment of inertia of an object, is. I'm going to stop this lesson here, on this part of the lesson. I'm going to take up another part for this lesson. We will continue discussing moment of inertia. Okay.